some functions so that we can start to describe what's happening. And we're going to be using this H's and K's is really where our focus is right now. So we wrote that standard form on the front page of our Unit 5 piece of paper where we were looking at H's and K's. I'm going to keep on referring to that. Based on what we wrote before so that we can see where our focus is each day. And different lessons are going to add a different layer to it. So today we're focusing a lot on the H's and the K's happening. And this one specifically, when we're thinking about vertical translations, is going to be looking at the K value. Now we just said that the H's, the horizontal change, moves opposite of what we think. So if we had an X minus a number in parentheses, that minus sign moved it to the right. We're going to find that our vertical translations, our K values, move exactly like we think they should. And you guys have seen this before already. You were already telling me that we could move some things down 2 units. And so by changing the constant in an equation and moving it to a -2, we would push the whole thing down 2 units. So our K values today are going to be moving things up if we have a plus K value, or moving it down if we have a minus K value. Section 2.2 gives us a graph to begin with. Graph of function g is a vertical translation of the graph of polynomial f. So we are starting with f, and we are moving it to g. Move f to g. This is probably our one biggest common error throughout the entire unit, is just knowing which one to start with and how we're describing motion. Because it won't be opposite if you go the other direction. It asks us to complete the table for column G in our table of values. So what was at -4, 0 here in the f function corresponds to our value here at -4, +4. So our input is still the same of -4, but our output has gone up 4 units. Our input at -3 in our new graph is no longer at -5.8. It still has an input at -3, but now the output is at -1.8. And I can tell that because it looks like every single output value is adding 4 to it. So our 0 happening at -0.7 is still happening at -0.7, but it's not a 0 anymore. It is slid up 4 units to be at a +4. So everything is just adding 4 units to it. It's sliding up 4 units. value, this thing that's outside here, isn't changing the input value. It's happening after our input. It's changing the output values. It's just sliding the whole thing up. So we have an input of 0 that has an output of negative 0.86. Our new value at g of our new function g at that same input value will have an output just 4 units higher. So we just need to take that negative 0.86 and add 4 to it. And we'll find that g of 0 is 3.14, which sounds about like 5. Thank you, Liv. I appreciate it. And the way that we know it is that it has just moved all outputs are 4 more than what they were from our original function. So if that's the case, if we're just taking every output and we're moving it up 4 units, we could take our g of x function equals our starting function, the one we began with, f of x, and adding 4 to every output value. So it takes every f of x output value and just adds 4 to it. Let me capture that thinking while you start looking at number 4, where it's going to take this same f function and the g function, and now we're going to have a third one, an h function, to go with it. So our h function, we can now look at the equation that it's giving us, and we can see what it's telling us to do. If we're taking our original function f, and we're subtracting 2.5 from the end of it, that means we're going to take that whole f function, and this time instead of raising it up 4, we're going to push it down 2.5. Now be careful with this. You now have a g function in the middle that we have filled in. It's telling us to go back to our original f of x function and subtract 2.5 to it from it. So we're just taking every original output from our f function and subtracting 2.5 from the output value to slide the whole thing down. On the next page, it asks you to take all of these ordered pair points and graph our new function, our new h function. So I'll keep my ordered pairs up here. Feel free to use mine as we start graphing, so you want to keep on flipping back and forth. But we're going to use our ordered pairs now to graph these. Input of -4, output of -2.5. Input -4, output -2.5. -3, -8.3, -0.7, -2.5. And so we're following the same shape of the graph. All we've done is translate it. And so our final question in section 2.2 asks us to write an equation for g in terms of x. Now g, if you remember, is our one that is much, much higher. Our g function is the one that was going way up here at 4, here. Right here. So if we're trying to write an equation for g in terms of h, this is our last question here in section 2.2. This means we want g of x by itself on one side of the equal sign. G of x. So if we're writing g in terms of h, we want g by itself. And then we'll use h as our starting point and then see how we're going to move some stuff. So if I'm trying to write g in terms of h, I start with graph H. And I need to figure out how I'm going to describe the movement to get from H up to G. Now I just said up to, so that means I need to slide it upward. I need to add something to it. How much do I need to add to get from an H output to a G output? I'm going to think, how much do I need to add to get from like a negative 2.5 up to a positive 4? How much do I need to add to get there? How much? 1.4? Oh, 5. Nice. So let's see. If we have this one, what was our function? Nice, 6.5. Nice. So this one we had to move it up 4. So we started at G, or started at F, and we moved it up 4. For H, we moved it down 2.5. So our total distance now between those two is a 6.5. So we'd have to add 6.5 each time to get there. So every single point, we had to add 6.5 to get from our starting h function now up to g. Our next portion, we're going to look at 2.3. We're going to go through it kind of fast because it's, it's got some neat stuff to it, and it helps explain a little bit more why some of those X's, the horizontal translations, move opposite of what we're thinking they should. We're just going to do a small part of it, though. Will you look with me at this part about heating the kitchen? So we've got a bakery kitchen that has a thermostat set at 65 degrees Fahrenheit. Will you start and find the 65 degree Fahrenheit temperature that is our starting temperature for the day? Put that point there. It stays at 65 until 5 a.m. when the temperature starts to rise to 85. So from midnight until 5 a.m., it stays at 65 degrees. Starting at 5 a.m., it takes an hour for it to rise up to 85 degrees Fahrenheit. So by 6 a.m., at 80, it's 85 degrees. And so it has taken some time for that temperature to rise to become 85. By 6 a.m., it's 85 degrees because they turned on all the ovens to bake bread. It stays at 85 until 10 o'clock. Baking is finished. And let's say it takes an hour for it to cool back down to the 65 degrees that our temperature is set at for the rest of the day. Nice. Chase is making some nice graphs. He's starting with the plateaus, and then he's going to connect some dots to get those rising temperatures and lowering temperatures. Veronica's got the same idea going on in her book. Nice job. If the bakery owner decides to change the shop hours, they want to move everything 2 hours earlier. Everything is going to shift 2 hours to an earlier time. So everything is moving 2 hours. Our new function would have everything 2 hours earlier. So maybe you want to draw it in a dashed line, or maybe you want to do it in an extra heavy line, what this new one is going to look like. So this is where the kind of where we have to kind of get that opposite thought process. Remember thinking about how our horizontal changes, this one's very much a horizontal change, and how we would have points that coordinate with each other. So, on our original graph, at 10:25, 10.25, it was 80 degrees. Ooh, goodness gracious. I'm going to have to calibrate my board. So put that point there on our original graph that we had a point at 10.25, comma, 80 degrees. That makes sense. They've turned off the ovens at 10 o'clock. About 15 minutes later, the temperature has started to go down to be 80 degrees. The corresponding point on the G graph, on our new one that we rewrote after they changed their hours, would be at 8:25 and 80 degrees. So the function notation to describe that is that it's happening at 8¼ hours. So G of 8.25 equals 80. This is what they mean by function notation. We're just saying what is our function that we're using, what is the input that corresponds with the output. And so here is the why this stuff is happening. Because these 2 points are corresponding to each other. If we're thinking about writing our equation G for time in terms of our H, we are still taking that 8.25, and because it corresponds with the same old time of 10.25, we have to add 2 to make that corresponding jump. That's why we end up with the +2 here. Now notice it's in parentheses this time because we're changing the x input versus our last one that had the plus afterwards that moved it up and down. So there's a big difference between this x +2 in parentheses and the +4 that we did in our last part that just moved our whole graph up. Okay, so function notation, we can use it to help us describe the change. And our new 8:25 corresponds with something that was 2 hours later on our original graph. So those points would have to add 2 to it to make it true. Lots of people think that in this situation, because we're moving the time 2 hours earlier, that we would just subtract 2 from it. But a -2 would actually shift our graph to the right, and we wanted to shift it to the left. You can see that every single point is 2 units moved to the left. So we can start writing these things in terms of each other, and we're going to see that we're not locked into just a single direction at a time. Capturing that. And now it's your turn to check your understanding with this. We'll come back and do our cool downs for 2 and 3, but this is our last section we're going to do in our workbooks together. Will you turn with me to section 3.1? We're looking at how we can translate graphs in lots of different ways and using left and right translations and up and down translations at the same time. Okay. Before we start, one of these graphs up here in the different colors. So we're going to start always with A and describe how we can get to all the rest of them. One of them we actually cannot do just with translations. Which graph, B, C, D, E, or F, can we not do just by simply sliding the A graph to a new location? If I slide it over, I can match it to B. Which one can I not match just by sliding? Well, I heard a couple different things. I heard some people say D and I heard some people say F. Let's hear the argument for D. Why can't I match it to D?
The one side is longer.
Alright. The top got longer for D. See if I slide it over here? It's got that nice match for our slope part, but the horizontal part, it stretched it. So D, we can't write an equation for. Go ahead and mark that in your book. That D, because it stretches this top, there'll be no answer for this one. The top got stretched. So I can't just slide it left and right. I can't by translation get it to match D. Can't do it. Let's try writing B together, and then you'll have a chance to try C, E, and F and see if you've got this idea. To write function B, we're going to use B of X. We're going to use function notation. B of X is our A of X function somehow changed. Which direction am I moving? Left, right, up, or down to get to B?
Right.
Alright, so I'm moving it to the right. That's going to tell me that I need to go to the R-I-G-H-T. I need to use an M-I-N-U-S. Inside parentheses. I'm moving it with my X. How many units are we moving it to the right? 6. Beautiful. So we have an X minus 6. Do your best with C, E, and F. Paying close attention to if you're making a change inside the parentheses with the X or outside the parentheses to move it vertically up and down. Give it your best try. We're going to check it in just a couple minutes. Bless you. All right, let's see if some fellow classmates can help us out. Alyssa, I drew your card. Would you help me out with what you wrote for part C? Being careful to tell me what's in parentheses and outside.
Okay, I don't know if this is right, but I did A and then parentheses X plus 3 and then minus 5.
And then minus 5. All right. Let's see. I like how you started with the A, definitely. I see we're moving to the left 3 units, so that plus 3 looks fantastic. P-L-U-S, we'll move it to the L-E-F-T. Nice way to remember that. And then down 5. Great example. Well done. Chase, would you help us out? What'd you write for E?
E of X equals A, and then just X in parentheses by itself, plus 6.
Plus 6. Nice. X in parentheses by itself, and then we're taking the whole thing and lifting it up 6. So we want the plus 6 outside of parentheses. We're not changing the X's at all. Beautiful job. I can tell we've got this A-okay. Kennedy, would you give us your... Oh, last thing. This is it. Hold tight. Kennedy, go for it.
So I said f of x equals an a in parentheses x minus 2, and then outside of the parentheses plus.
Very, very nice. All right. So we've got some great ideas of how these things are moving side to side, up and down. Nice job. Thanks, friends. Take a look at practice lesson 2